Yeah, so I think Kenneth gave a great introduction to all of the things we can do now with so many neurons. He hinted at some stuff that I'm going to talk about, so I'm glad I can go a bit more in details. The main focus is going to be on looking at the timing of neurons relative to external things and internal things. Okay, so I'm just going to unpack that a bit. So that's the outline. Just to give you a little bit of background, I'm going to start here with this image, which is a classic of what you're going to end up with if you record with Neuropixels. So you have, let me just have my pointer. Sorry, where is my pointer? Here it is. Okay, you should see it. So you have a raster of activity. Here you have all the neurons on the y-axis and the time on the x-axis. And you can see there's a level of organization during the spontaneous period, but also when you present an image, you can see this increased activity. And basically what I'm going to talk about are the very basics of how you can try to understand how the activity is coordinated across neurons and across time in response to these images, so to external events, but also in response to internal events. And here I'm going to take the example of population rate, which Kenneth has talked about just before, but I'm going to reintroduce it. All right, so what do you start with? Just to go back to the basics, usually what you end up with after spike sorting are two or three actually vectors. The first one is for each spike. Okay, so each of these values is associated to a spike. You have the cluster to which it's associated, meaning the neuron that emitted this spike, and also the timing of the spike. So that's what, for example, kilosort is giving you as an output. Another vector you may have are the events, the external events that you may be interested in, like when you present an image and so on and so forth. And what do we want to do? There are two main things here I'm going to talk about. The first one is looking at the firing of neurons in relation to external events. So, how do you align everything? How do you look at these PSTHs that that Kenneth has mentioned? How do you process it and so on? And look at the firing of neurons in relation to internal events, which is something that we do more rarely, but that is also pretty interesting. Okay, so to start with the simplest one, activity logs on external events. So the first thing that you need to do, and here I'm going to go back to, I think, something that have been mentioned in the first day of the course, which is aligning signal. What we do in the lab to align the spikes, so the EFIS data, to the, the stimulus data, we use what we call a flipper. So we're going to have an Arduino, for example, generating a random signal that looks like this. It's an electrical signal, like a binary electrical signal, that goes up and down at random times and really fast. And you see these transition times are going to be the important ones. And you send these signals to two things. You send it first to the data acquisition system where you record your EFIS. So you will know the relative timing of your spikes, the timing of your spikes relative to the flipper. And you also send the exact same signal to the Steam acquisition card, where you will record also simultaneously the event times. And these may be two different computers. For example, here in the lab, it's very frequent to have it on two different computers, because that's one thing that we use. And what you want to end up with is to align these two things so that then whenever there's an event, you know that it's happening in between these two flips, and you know it's corresponding to these different spikes. Okay, and why we have to do that is because if you record things on different computers, they may be recorded at different clocks. Okay, because computers have their internal clocks that are not absolute. And just to mention, one way we, at least in the lab, we prefer to align things is to use interpolation instead of just a linear fit, because you could just squeeze the signals with an affine function. But actually, interpolation may give you a better approximation. So that's basically, what you do. You interpolate what's the exact timing of this spike or this event in this time frame or this time frame. Okay, and that's because sometimes the time compression, let's say, can vary over time itself. Anyway, let's go into the details, but that's something you need to keep in mind. So this is what you start with. Again, the spike clusters, spike times, and external event times. And if you want to build your peristimulus time histogram, which is the very classic thing we build when we look at stimulus responses, you may want to wonder about a few parameters. The bin size. So it's the size of the bin that you're going to use to look at your data. So in my case, I'm going to take 4 milliseconds. The overall window that you want to look at around the stimulus. So here it's going to be -25 to 250 milliseconds. but also some smoothing to make the data a bit less noisy, let's say. And so you start with something where you have your spikes, you have your events here, and you want to end up with the raster here that, and Kenneth has mentioned that, where, this is time around the event that is represented here by this vertical line. And each row here is a trial, and that's for a single neuron. Okay, so this is a raster where each dot is a spike. This is the very classic thing that you look at. This is what Kenneth presented, and his very good suggestion is to actually, you can sort this raster depending on, the time during at which it was presented. You can sort it by image, obviously, if you're interested in, what kind of image it responds to. I'm in visual cortex here. I didn't tell you. You can sort it by whether the mouse moved or not, and so on and so forth, okay? And the way you do that is literally you take every one of these guys and you look around the little window that you decided here, you bin it with the bin that you chose, so 4 milliseconds, and then you make each of these rows. And then you can take the average of that, and it's going to look like this. So you have a nice response here with a little second bump, and that's for one neuron, and that's basically the PSCH. There are a few parameters you can change to smooth a bit this. So let's say we take this matrix and we smooth it with some Gaussian filter. In that case, the Gaussian filter was 1 bin, so basically no smoothing. But you can increase it, so 5 bins, 15 bins, 30 bins, and it depends a bit on what you want to see. But be mindful that the smoother the bigger the filter, the smoother it will be, obviously. But also, you're gonna get some temporal absurdity, let's say. Like, for example, here it starts to respond before the stimulus, but that's just because of the smoothing. Another thing that people do that I've heard is use some causal filter to avoid that. So you remove the first part of the filter that's creating this kind of increased activity before it actually starts. And you don't get that anymore, but then it shifts activity a bit. Okay, so I wouldn't use that, but I'm just mentioning it because I've heard some people use it. So you can play with this smoothing parameter. Another thing you can play with is the size of the bin. So here it's with 4 milliseconds, and here I moved it to 8 milliseconds. You can see it may look a bit nicer. So this is up to you and what you want to see. Okay. So one thing that we can get by doing that, and I'm showing here, is basically we can try to investigate, for example, whether each neuron is responding to images, in my case, visual cortex, at a specific time or not, and whether it depends on the image. Okay, so here, just to illustrate that, I'm showing 3 different neurons. So you have neuron 1, 2, 3, and I'm showing their PSTH. So that's basically, this response here that I showed before, to 3 different images. And you can see that for neuron 1, the timing of the response is kind of always the same. It responds at the beginning, but the size of the response is going to change with the image. Okay, so it's encoding which image by the tuning, so by the frame rate, sorry, but the timing doesn't change. This neuron is the same thing. The amplitude of the response varies with the image, but the timing doesn't. And actually, it's coming a bit later than this neuron. Same for this neuron, which is actually coming last. And here it does not really encode which image is on the screen. Okay, so that was for 3 different images. You can also show many different images, like about 100. And you can see that these 3 neurons actually, always spike at the same time, but encode the image. So on the y-axis is the image, but encode the image by their overall amplitude, especially for this neuron here. And then you can play a bit more with this. I won't go into the details of that, but if each neuron has a single time course and that is modulated by which image is being displayed, you can actually summarize it here by looking at the center of mass of the response. So it's basically where are the main spikes, where is the main bulk of the spikes here on this PSCH for each image. And this is for the 3 different neurons that we're looking at. And I've cut the data in half to look at how reliable it was. So I'm taking odd and even trials to compute that. And each dot is an image. And you can see that, each neuron is always spiking whatever the image around the same time. And that's actually true for all neurons. What that means in the end is that we can predict what the activity of the neuron is going to be with a very simple model that just takes into account the time course of the neuron that you're going to weigh by the tuning of the neuron, so just a single number per image, okay? And you can see that it's predicting very well what we have. So it's just a very simple summary of what how a neuron can respond. And if you put all the neurons together, you can already see it here, that they start to form a nice sequence So here I'm putting all the positive excitatory neurons, positive inhibitory neurons, and they form this nice sequence overall. Okay? So now that was activity locked on external events. Another thing to look that we are interested in and that Kenneth mentioned at the end are activity locked on internal events like the up and down phases. And if we go back to this is actually something where we focus here on what's happening on that part of the recording where nothing was on the screen. And this is basically the reason why we're interested in this is because the neurons all together form some kind of an orchestra, and each neuron in this orchestra is going to have a specific role, let's say. The first one and we're going to focus on that role in relationship to the population rate, but you may also look at the pairwise relationship between neurons. Okay. The first one of these roles is whether they are choristers or soloists. This is something that's been described by Michael O'Kuhn in Nature 2015. And basically, this is when you take the cross correlation or some sort of cross correlation, I'm going to get into that, of each neuron with the population rate. And you can see that when you do that, this is the cross correlation of that neuron or the cross spike triggered population rate, actually. And you can see that each neuron that is depicted by a different color may be more or less coupled to the population. And the size of this thing is telling you whether they're a chorister, they spike with everyone, or they're a soloist, they do their own thing. And actually, whether a neuron is a chorister or a soloist, which is represented here on the y-axis, each dot is a neuron, during spontaneous activity is also true. So the same neuron is also going to be a chorister or a soloist during evoked activity. So you can start to play with these things across context, try to see if this is a more general property of the network or not. That's one thing. The second thing, and this is more linked to the title of the talk, is about the timing. Kenneth did not mention that, I don't think so, but actually neurons form a sequence that I've just mentioned before, but also during spontaneous activity. Okay, so if you look especially on these up phases, so that's locked on the up phase, each row here is a neuron and different trials for each neuron, you can see that they form a nice sequence. And this sequence here, this is in auditory cortex, is the same during onset of a tone and spontaneous. All right, so how can you quantify that? I'm just going to introduce very briefly here a little math of little notations. I'm going to denote f of I, the firing rate of cell I, and the sum of all the f's is the population rate. Okay, and actually I'm going to exclude neuron I because I don't want it to pollute the population rate if I want to take the correlation. And you can look at how much a neuron is coupled to the population in two ways, either by computing directly the correlation coefficient. So that's just the classical value of correlation coefficient. You take the firing rate, remove the mean, do the same thing for the population firing rate. So you want to correlate, cell I with the population, and you divide by the standard deviation. Another thing that you can do is to take the population coupling, which is equivalent to the spike-triggered population average, where here you won't remove the mean, and you have a slightly different normalization. And I'll show you why you may want to be interested in using that compared to correlation. All right, so let's start with correlation, sorry. Again, you're going to have a few parameters that you may want to play with, and the first one is the bin size. So this is your neuron. It's been binned with a 1 millisecond bin, so it's either spikes or not. And this is the population rate. And I'm going to show you here for many different neurons the histogram of the value of the correlation between each neuron and the population. And you can see that it's very well centered on 0. Most neurons have very low correlation at such a fine time bin. When you increase the time bin, so you can see here you start to have many spikes per bin, you change that distribution. So depending on what you want to see, you may want to change really the binning of your vectors. And when it's really large, you start to have really high values of correlation. Okay, so now if we go back to a 1 millisecond time bin, actually one reason why here I told you about this other technique that is the population coupling and not population correlation is because population correlation, so the correlation of each neuron with the population, which is on the y-axis, each dot is one neuron. In red are the inhibitory cells or putative inhibitory cells, in black are the putative excitatory cells. So the coupling of this neuron, when you measure it with correlation, is very well correlated to the firing rate. So the more neuron fires, the more, at least with this measure, it seems to be correlated with the population. So that's why we can use another measure, which is the population coupling, where here the normalization is slightly different, and you don't remove the mean, although this is less important. And when you do that, actually, this is again the histogram. You can see that it takes different values. And just to go back to this idea of the orchestra, you have here the soloists, which are poorly coupled to the population, and the choristers, which are highly coupled to the population. And when you plot it as a function of firing rate, here you see no correlation. Okay, so you factored out the importance of firing rate from this measure. Okay, and the coupling and the correlation with the population rate are correlated, but not entirely the same. All right, so that's just to present you the different tools you can use. Now, very importantly, when you're interested in timing, what you may want to do is actually to shift these two traces with different lags and build what we call the cross correlation. So you'll have different lags, and you'll measure at each of these lags the coupling with the population rate. And this is for one neuron, what it looks like. So it peaks around 0, and then it goes down on both sides, although it's slightly skewed towards the left. And then these are for different neurons, and you can see that the size of this changes. So that's whether the neuron is a soloist or a chorister, but also whether it goes on the left or the right. Okay, and I'm going to extract here the slow component and not look at the fast component. That's another thing you can do. You can filter these cross-correlograms or cross-coupling plots to extract the parts that you're most interested in. And actually, when you put all the neurons together, and then I should wrap up, you can, and Z-score them to avoid looking at the overall size, but just focus on the timing. You can get these very nice sequences. So that's what I showed you at the very beginning, except now it's in visual cortex, that happen during spontaneous activity. And they're very reliable. This is when you take the center of mass of these sequences on the first half and second half of the data. Very reliable. You can also see them in single up phases, as I showed you at the beginning. They also happen, when you present a stimulus. So this is bringing together the two parts of my little talk. This is what I showed at the beginning, except I reordered this sequence based on this sorting, and you can see that it's shared. And actually, if I plot one versus the other, you see that they are really correlated. So the same neurons are going to fire almost at the same time, whether there's an image on the screen or not during spontaneous activity. And finally, just because I gave a talk on chronic recordings, I just wanted to share with you that these sequences, they're actually very stable across days. So this is, the same sequence on day 1 and day 2. We've tracked the neurons using unit match. Now you know all about it if you follow the 3 days. And actually, if you compare, these two sequences, they look exactly the same, or up to the noise. And if you do it even across many days, so you compare recordings that are 1 day apart, 15 days apart, 30 days apart, and you compare these two things. So the closer to 1 is very similar. You can see that this is a very stable property of the network. So just to wrap up, sorry I'm a bit late, but on the first part, if you're interested in activity locked on external events, here I'm just going to give you the scientific results actually, but you have some tips on how to do it and things that you may want to pay attention to. But neurons here in visual cortex, using these tools, we show that they have a characteristic response time course. And finally, we can also look at these locked on internal events, and these time courses and activation sequences are also found in spontaneous activity. And with that, thank you very much.